the differential equation of time domain form is transferred to the algebraic equation of frequency domain. In other words, we can say the Laplace transform is nothing but a shortcut method of solving the differential equation. Now, here, if you will see the overview, and we can identify the definition in the proper mathematical form. So basically the Laplace transform will take a positive real variable t to the time to a function of a complex variable that is in the frequency domain, that is s, or we can say the j omega, where omega is nothing but the angular frequency. In mathematics, the Laplace transform is an integral transform. Okay, and it is named after the discoverer of Paris-Simon's Laplace. Next, what is the Laplace transform? If you will see the yeah, if you will see here the our function, if our function f of t, if you will take any function which is f of t for the real variable, and you will take the Laplace of that f of t, that Laplace of f of t is converted to the f of s. F of s means what? That is in the frequency domain. So as per the definition, it is the integral transform. So you can see that is the limit is from 0 to infinite. Your actual f of t function multiply with e to the power minus st, and this e to the power minus st is called as a kernel. So if suppose we have any function like unit step function, impulse response, or any type of exponential function, if you will take the Laplace of that function, so that is converted to the f of s, and this f of s is 0 to infinite actual original f of t multiply with e to the power minus st. Apart from that, if you will take the some of the simple uh, function, so we have a unit step function, we have an impulse response function, and we can transform for the impulse response to the first derivative. So like this we can do the some sort of solutions. So for example, if you will take a first function that is called u of t, and this u of t is called as a unit step function. If you closely look at the blue line, the u of t having two values, one is 0 and second one is 1. So when the t is less than 0, you can see t is less than 0, the value of u of t is 0, and when t is greater than 0, the value is 1. So we can say the function for the u of t, it is having two values, 0 and 1. Apart from this, we have some sort of properties which is called as a time shift properties and time reversal properties. So here, if you will see, this is our the 0, our time is shifted towards the a. So we have from the a point, that is the 0, mm, uh, that is the 0, and the second one is 1 level. So for this case, we can write as a function f of t is k u of t minus a, and for the time reversal, we can write k u of a minus t. Now, now we will take a unit step function and we will try to calculate the Laplace of that. So first of all, we'll take a function of u of t which is having two values. One is t is less than 0, it is a 0, and t is greater than 0, it is a 1. When you are taking the Laplace of u of t, as I told, that is the integration of 0 to infinite u of t e to the power minus st. Now this u of t having a two value, one is 0 and second one is 1. For both the cases we will take. So for the case of 0, it is completely becomes 0, but for the case of 1, it is 1 multiplied by e to the power minus st. If you will do the further solution for e to the power minus st, it is become, you can see here, yeah, it is become as 1 by s. So in short, or in short, we can say when you have the unit step function and you are taking the Laplace of unit step function, it will become 1 by s. So likewise, we will take exponential function. So here you can see the exponential function. When the t is less than 0, the function value is 0. When it is greater than 0, e to the power minus 80. Now we have to take the Laplace of e to the power minus 80. So So for this case, if it is a 0 to infinite e to the power minus at multiplied by e to the power minus st, it is become, if you will see the final solution, it is become 1 divided by s plus a. So in short, we can say when we are taking the Laplace of exponential function, any exponential function, so that is become 1 by s plus a. Likewise, if we will take the function, for example, the sinusoidal function, so this is actually, you can see the waveform of the sinusoidal function. So when you are taking the Laplace of the sinusoidal function, so it will become 0 to infinite sine omega t multiplied with e to the power minus st. So we can write it, we can finally see the property after doing the complete solving. It is omega by s square plus omega square. Likewise, we will do the we will take the example of cosine function. Then again, the Laplace of cosine function will s divided by s square plus omega square. So with the use of first of all, with the use of some of the functions, we can apply for the Laplace transform. Then we will get a solution in the frequency domain. So this Laplace transform, now you can see, if you will take any function as an input of circuit, that particular will give you the solution in the in the frequency domain. After that, we have to convert to the again time domain. How to convert to the time domain? If you will take the inverse Laplace, it will automatically convert to the time domain. So based on that, we have some sort of properties that is called as the Laplace transform pairs. If suppose f of t is del of t, it will become 1 in the frequency domain. Then u of t, it is become 1 of 1 by s e to the power minus at, it is 1 by s plus a. When it is a t, 1 by s square t to the power n, that is factorial n divided by s to the power n plus 1. Then we have the property of sine omega t, omega divided by s square plus omega square cos omega t, s divided by s square plus omega. So these are the some few properties which is very important to solve the problem in the using the Laplace transform. The one more thing is e to the power minus at cos omega t is become omega by s square plus a whole square plus omega square, or e to the power minus 80 cos omega t s plus a s plus a whole square plus omega. So these properties are very important to do the solution in the frequency domain. If you have any circuit, we can use as an input for the f of t signal, then we'll calculate the output. Now if we have a one gate function, so easily we can do the solution here. You can see the solution is very simple. This is the property of time shift property. So 10 is nothing but our the actual magnitude of that signal, that is u of t minus 2. You can see that is from that one maximum value in the 2 between 2 to 3. So that is t minus 2 minus u of t minus 3. Likewise, some of the example we have taken here, which of these expression describe the function plotted here. So we have to do the solution. Maximum is 5. So this is shifted towards the 15. So very simple, 5 u of t minus 15. Correct. So likewise, we have to do the complete solution. For example, this one we can do the solution. This is also we can do the solution. Then so after getting the idea of the Laplace transform, we have to go to the inverse Laplace transform. This is nothing but just whatever you have a signal in the frequency domain, the output in the frequency domain, if you will take the inverse of that, it will convert to the time domain. How to convert to time domain? You can see, if you will take the inverse of f of t, so the inverse of 3 by s, nothing but it is 1, that is 3 multiplied by u of t minus Laplace inverse of 5 s plus 1. It is 5 multiplied by e to the power minus t. Likewise, Laplace inverse 6 s square plus whole square 3 sine 2t. Next, for example, this is, you can take this example. So we can use here the partial fraction method, a by s plus b by s plus 2 plus c by s plus 3. So if you are taking the inverse of this, first of all you have to calculate the value of a, b and c. So how to calculate that value of A, B, and C. For that, we have a residue method. Everyone knows what is the meaning of residue method. Here, very simple. Simple. A is using that method. A is 2, B is -8, and C is 7. Apart from this, we can go for the algebraic method also. Okay, so algebraic method also we are getting the same value. A is 2, B is -8, and C is 7. So now our main focus is on how to apply the Laplace transform in the AC circuit, because we are talking here about the AC circuit. So we have three very important point we have to remember. The first one, transform the circuit from the time domain to S domain. Solve the circuit using nodal analysis, mesh analysis, source transform, superposition principle, or any circuit analysis technique with which we are familiar. The third and most important, after getting the complete solution, definitely we have to convert our solution into the time domain, because our solution is in frequency domain. Then again we have to take the uh, convert into the time domain. How to convert? We will take simple the Laplace inverse. Now, so our work will start from the lumped element, which is we have the resistor, inductor, and capacitor. If we will take the resistor in S domain, so first of all we have to recall the IV relation in the time domain. So IV relation in the time domain is V of t is equal to R multiplied by I of t. Now the thing is, by taking the Laplace for this, so L V of t, so L R I of t, so that is the small v of t is become capital V of s. This R is actually the R value. Then Laplace of I of t is nothing but your I of s. So in conclusion, we can say when we are taking the register in the uh, S domain, so there is no change in the register value in the sorry, when we are converting from time domain to S domain, so there is no change in the register value in frequency domain. Apart from this, if we will take the inductor, so we know the IV relation. IV relation in the time domain is V of t L di d by dt I of t. So that when we are taking the Laplace of this, so Laplace of V of t is become V of s. Then for the d of t, it will come to the first derivative. So here the one very important parameter which is coming to the picture, that is called I0. This I0 is nothing but called as the initial current. Okay, because we have two different conditions. One is t is less than 0, t is greater than 0. So for the initial, how much we have a current, so that is the reason we are writing as L multiplied by is minus L I naught. So for this initial value, for this initial value, when we are converting from time domain to frequency domain our circuit, definitely we have to take into the account. So if you will see the equivalent circuit model of inductor in S domain, so when we are converting, so you can see here we have a two different cases. As I told, that is one very important parameter which is coming to the picture for the case of inductor, that is called the I naught. So when we are converting from time domain to frequency domain, so this is L is nothing but SL, and we can add the voltage source in the series. Why we have to use the voltage source in the series? Suppose the I naught value is 0. I naught value is 0. So for that